Pause.
Einstein-Uhlenbeck process, given by Brownian and Norton, standard Brownian. Semi-group. This function in our world of time and space. Time, what do we observe? The observer, some sort of function, assume any boundedness or structure. And this is our starting time by observation or initial position. So one negative number, element to another, we are in diffusion. And we are blessed exactly because we have this particular process. We can write this as explicitly as we can imagine. Gamma here, gamma is the invariant measure. It's a Gaussian, anti-Gaussian measure. With this as its density, the Gaussian density function. look at this like the apple of our eye, right? The nabla of this scalar function is minus y, which is a vector, times scale. You can look at all of this if we are doing this as an extended exercise and by parts, and this saves us each and every. We have the Dirichlet form for two functions f and g, bilinear, linear in f for fixed g, linear in g for fixed f, x. So you pay up the gradient of f and the gradient of g, and you integrate with respect to the integration by parts, then you can write this equivalent like this. L is the generator. L is the generator. And it's a negative operator in the sense that minus L of the integrated respect gamma is to something very close. So L is a negative operator in positive operator. This is the bilinear Dirichlet form, and this then is the Dirichlet energy, right? How much energy is there? Okay, we have other commercial identities and inequalities here, but the most celebrated are these. The variance with respect to gamma, any given function f, is no more than the Dirichlet energy. This code by the name Poincare. This inequality we proved. We went through the proof, actually in some detail. Now we have an even greater inequality, which goes all the variance is dominated by the Dirichlet energy, and then the entropy of the function f with respect to gamma is dominated by 1/2 the Fisher information. The Fisher information being this. This is not a definition of Fisher information we gave in class, but we discussed last time that if you play a little bit with this definition, you can bring this expression into the definition of relative entropy of Fisher information we gave. This goes by the name of the great Soviet mathematician Log-Sobolev. Yeah. This inequality is usually attributed to Gross, Leonard Gross, for 1975. But as a matter of fact, a guy in University of Michigan by the name of Federbush had derived this inequality himself a lot earlier, 69. So when I gave a talk at the University of Michigan right before the pandemic, I was prepared to talk about these things. They warned me, Federbush is going to be in your audience, so don't refer to don't refer to the Log-Sobolev, by terms of cross, mentioned also Federbush, and he was very pleased. Yeah, that's right. Yeah, all right.
Did Federbush publish it?
Oh, yeah, it's in there, but it was forgotten somehow.
Okay.
And then, what's his name? Leonard Gross made a big splash. And for a while, nobody was talking about anything but Log-Sobolev and this and that related to it. I'll tell you some things about it, but a lot of credit should go to Federer. Let's try to mention here. We should also mention Gross, because Gross did a lot of stuff. He understood the significance of this thing a lot better than anyone else. So he deserves it. An equivalent way to write the Log-Sobolev inequality is, I mentioned recently. Yeah. Very pleasing, aesthetically very pleasing way to write this, is to write it like this. Write it not for f, but for f squared. If you write it for f squared, look at the entropy of f squared, in other words, you make a 50% discount. Then this is dominated by exactly the same upper bound as in the Poincare. It's another beautiful way to write the Log-Sobolev inequality with the same upper bound as the Poincare. And this tells you that the total energy, the finished energy, right, controls both the variance and the entropy, well, the variance of the function and the entropy of the system. All right. We can go with proof Poincare. Let's prove Log-Sobolev. First proof is very yeah. First of all, what can I go?
You can go to the.
I can go up there. Let's see. Oh, listen, come with the definition of the. It's the usual definition of entropy, F log F integrated against the measure. But here I normalize the second F and solve the local well. So I take a positive function F, I integrate it with respect to gamma, and then I normalize F itself, right, relative to its mean. This marker this becomes integral of h of f with respect to gamma minus h of the integral of f with respect to gamma. H is this one. X log x. We all know that this function is convex. So, well, again, this is a non-negative point. Again, this is a non-negative. So at least we don't pretend to give a positive upper bound or a negative point. In other words, we're not completely ridiculous. So this is the definition. Some blackboard management. When you start teaching, you realize that blackboard management is an art. And you master it only by doing it. Yeah. Let's see. What will be the following? First observation. Make some cheap observation. P0 of f is f. In other words, the function. But P infinity of f is what? The infinity of f is the integral of f with respect to gamma. The guy I just this guy. This guy. So P0 of f is a function, but P infinity of f is a it's a number, it's positive. So let's keep that in mind. And then we have the most-inaudible flow, right? Starts the function, and then goes all the way to infinity to a number. This is a manifestation of the fact that it's an invariant distribution. It converges, right? It starts no matter how it wants to start, but then it goes, right? It equilibrates to the station, the distribution of time, which is. So let's keep that in mind. Let's define this origin. What I like about these groups is that they're completely evident. It's my government doing anything. Yet we get deep results. These are deep. In terms of this function, time, I fixed it, and I fix it on negative. Was it? Now this is a function. In terms of this flow, temporal flow, the entropy is just the beginning minus the end of history. So introduce this flow with the minus flow. Want to write the entropy is the flow 0 minus the flow. Which means that I cannot write is an input now. Wow. Now I say, let me compute the derivative. We're not going to worry too much about passing derivatives inside integrals. We leave that to the first semester of analysis. And probably, yeah, we have graduated. We have graduated. In other words, you assume all you need on the function f so that everything that we do here is good.
We do and then we vector it.
Yeah, we do. First we do it and then we just. Right. So now I differentiate. So set that one. By the way, this is the function h. I wrote the moment. Then I pass the derivative inside. Then I differentiate this with respect to time. What's the derivative of this with respect to time? It's the generator. It's the generator. If I differentiate bt of f, that's the whole point of the generator. The generator is the derivative, the temporal derivative of the semi. What's the derivative of this function? So I have one, then I have the log. If I concentrate on one, I'm integrating L of PT of L. But what's that? Zero. Why is it zero? Because if I take G to be a constant, the gradient of a constant is zero. If this is zero, therefore the integral of L with respect of any function f with respect to gamma is zero. So the constant here, the one here, is irrelevant. Because the integral L of a function with respect to the invariant measure is zero. Try to justify it from first principle, not from, which has a moral obligation to be zero. So to make a long story short, instead of h prime here, I might as well write log pt of f. So I'm integrating log pt of f times L pt of f. What is this? Well, I don't know. We have this to guide us. So I apply this. F replaced by P2 of F, and here G replaced by log. So I apply this. Poincare. I forgot the minus. What's the gradient of log? Eh. It's the gradient of the guy divided by the guy. Oh my God. Here. What is this? The fish. We have already a small jewel. Here's the small jewel. The entropy along the flow decreases.
In the Fisher information definition, on the denominator, we have x squared. Should we just have x?
F.
Okay.
Very relative entropy, according to the second law of thermodynamics, decreases. At what rate? Well, the rate is exactly the Fisher information. At the point of the flow. This is a famous identity. Maybe I have mentioned it, maybe not. We credit information theory the name of Shannon, Bob Shannon. Is 47, 48, 49, I don't remember. Bell system. So, Claude had a great idea, but he didn't do it. He had great insights, this, that, but he didn't do it. The guy who started proving information theoretic inequalities and establishing things rigorously and well was this Dutch guy, Stam. 57 or 58, 10 years, 10 years ago. So in a sense, the beginning of information theory as a field starts with that. Well, I'm exaggerating, but not quite very much. In that paper, Stamm has this identity, but he doesn't want to take credit himself for it. He attributes it to his teacher, the Brown. I don't remember the Brown's first name. The Brown was a great mathematician. He worked on many things, algebra, number theory, analysis, he could do it. So Stamm was De Bruyne's student. In that paper, he credits his teacher with it. De Bruyne didn't want to write. Yeah, okay. So, but this is called De Bruyne's idea. Don't remember what he did. Why? So now we have this. Can I go there? Not quite.
I promise we'll get a little wider screen and something. I know this is not a lot to work with.
Let's go to sacrifice. Well, sacrifice. Don't tell me we have done anything difficult. Make a long story short, repeating things that I just today. You probably agree with this, don't you? If the derivative is right, then this is just the integral of the how do we call it? The Fisher information. Fisher. If we remember the definition of the Fisher. We have a vote of confidence. Now I want to submit something to Parliament for another vote of confidence. I need this bit.
No, okay. Did you just say half in that last one?
No. This is the Fisher information. The half. Well, is a 50% discount.
Oh, okay.
They deploy it. But the Fisher information is this. The yellow goes up to here.
Okay.
Yeah.
Sorry.
Yeah. So let me try to get this right. Here is the Look at your Stein-Uhlenbeck semi-group. And tell me if you believe what I'm about to. Okay. Do I have a vote of confidence? Just differentiating that expression with respect to x. So this is the gradient with respect. Which means this. Which also means this. But P sub T is just an expectation. If you believe this, you have to believe also this. And you look at this and you despair. What am I going to do with this? The whole point is never to give up. We never give up. So we look at this. It's the expectation of the absolute value of the gradient acting on the cardinal coefficient. So this is just enough. Now what? She's facts. Because I have a product, I have the expectation of a product. So she's facts tells me that this ain't going to be any larger than the or the square of this ain't going to be any larger this. In other words, I take this boy in the denominator. Similar to this. This other gases. This upper part. Now I go here and estimate with an upper estimate. But what is this? It's the inside integral. I'm integrating with respect to space, and I have time as a parameter. Do I? It's invariant. I'm integrating with respect to the invariant measure. So the temporal parameter I see there is an illusion. I see it, but it doesn't exist. Why? Because I'm integrating with respect to the invariant measure. And if I'm integrating with respect to the invariant measure, I get something invariant. It don't depend on time.
It is zero.
Pt is P0, but P0 is the function. So I might as well replace here T by 0. If I replace Pt by 0, I'm left with a function here. But if I'm left with a function here, I might as well put the dt there because there's no t. There's no t. But if I put the dt here, what do I have here? What is this? It's almost a joke. Therefore, they don't tell me we did something hard. Yet, through these trivialities, we got to get over it. That's the job of mathematics, to make everything linear. Et voila. Now, let me try to illustrate how important these are. Do the following. Tell me when I can do it. When we say that diffusion like this is an invariant distribution, what goes unsaid most of the time is that it's, if it starts anywhere, it's settled. Eventually, we will. One way of this settling down is the decrease of relative energy. Second goes or the increase of energy. But there are other ways to understand this. There are ways to show you the difference. If things settle down, then the variance should go to zero. Or the relative entropy should go to zero. Ah, of course. And the next question. How fast? You'd like to know not only that it goes where it has to go, but that you don't have to wait till kingdom come, right? Forever. This is really what no, we have all the we have developed all the things without even mentioning. Of course, Poincare can't underlie. Yeah. I can't even read the plan. Or the Parmesan. As the French language. Yeah, I didn't even read it. So here comes the rigor. The diffusion like constant the decrease of relative entropy in the period, the temporal decrease is exponential. It's not a trivial result, but it becomes almost trivial if you have the Poincare network, if you know the Poincare network, if you know the Log-Sobolev. Let me illustrate at least one of these. I'll prove this. I'll prove this in the same way that you do. And it's instructive to do this. It's instructive to do. Let me try. Remember how we wrote this last week? We did something very similar to what we did today for relativity. We wrote the variance. It's like gamma. There's BF of 0. BF infinity. BF will be 4. On binding ourselves a little bit to appropriate of is the infinity. Then we wrote this. It's just reminding you. We like this, not for F, but for PQ. What's this? It's this. Except I write it not for F, but for PQ. So what is P0 PT of F? PT of F. integral f given. In other words, this is just this. Minus this. Square of the integral. Or if I differentiate, the derivative is going to affect only. What's the derivative of this? How do we compute the difference? Then last time we also no. I appeal now. Here is what I appeal. And apply comparison. Apply comparison. Poincare. Here is where I apply Poincare. Here is where I apply Poincare. If I baptize this function, if I give it a name, g of t, then this inequality tells me that the derivative of g is dominated by -2 of g. And g is a positive function. If instead of inequality here I had equality, I could bring a high school kid, right? Come here, kid. This is the simplest ordinary differential equation imaginable. Then the kid, without even looking at me, he writes down the solution. He writes down the solution. That's just a kid, eh? We don't need nothing. But we don't have equality here. We have an inequality. And then we forward our needs and we say, hey, if we make a discount here, can the same discount apply later, right? This is a famous, an important inequality analysis by the name of Gromov. Gromov's inequality says, yes, what the kid wrote down with equalities, it survives. If here you have an inequality, then the inequality survives. If you open any book of analysis to find differential equation, you cannot do differential equation without really good. So Gromov's inequality gives you exact. And in a very similar manner, we prove the exponential decay of the relative the entropy using the Log-Sobolev inequality. So my point is that if at some level these inequalities look a little abstract, they are almost a joke to do. There is nothing very clever about it. But abstract as they may seem, they are very, very good. And here is one in particular. Let me give an average. By the way, in exactly the same form, with tremendously low growth, these inequalities survive in the context of Langevin protocol. It's murder. It's murder. Here it's almost a joke. And I don't have to argue very hard to make it. Just remember how the Langevin protocol semigroup from the assignment looks vis-a-vis this. This is the truth. The other guy looks like murder. This is the easy case. Nevertheless, these two friends, this story and extended into the social network. Fantastic difference, which for some reason only the French. They published in a very obscure French. In French. 20 years ago, the French book such as the sample many ways. They couldn't, they looked very down upon Frenchmen who dare to speak English, with even more writing. So for those reasons, they published a very important, fantastic piece of work. En français, and in a publication meant only for friends and relatives. In very typical French. That's the idea.
I mean, I thought that was the case in like 1905, but
It survived, it survived. I was a couple of summers later. Jacques Neveu, remember Neveu, the book that I did? Jacques Neveu was the Pasha of Vilayet. And he comes to my office in fury. Did you hear anything about secrets? Oh, I says, like, if I had read it, it would have been secret. It is an attempt to organize in a conference or something secret without only for friends and relatives. I want you to know everything is open. If you hear about anything, just go. Nothing is secret. Yeah, they would even organize seminars, events only for chosen a few for themselves. Yeah, that persisted until then. Of course, 10 years later, everything was proper. Yeah. The Macri and the two, they have this amazing, and Gentil, they have this amazing book. This is explained. And it's a story. Still back in the mid-80s.
Argue.
Good book.
Oh, yeah.
Okay, so these two guys extended all of these things for Log-Sobolev with the potential function C.
The gradient.
Yeah, they take the gradient of some psi, but that psi has to be strictly convex. In other words, the Hessian has all its eigenvalues bounded away from zero. So there is a common positive constant which bounds from below all the eigenvalues of the Hessian. Under that condition, everything extends. But the proof is murder. Maybe at some point we'll go with some of the things. I started to say something, though I don't remember what it was. And then we got into the stories.
You're talking about the secret society, everything is open, somebody came to your office.
Yeah, no. Exactly. But what was I trying to say?
Not useful.
Let's see. I'll yeah. Now so like I was saying, Poincare and Log-Sobolev extend in Log-Sobolev some in special cases even beyond. So now I'm going to ask you to believe that for some diffusion we have a Poincare Log-Sobolev, in particular Log-Sobolev. So I'm going to do this because I think I can say a few things without being completely comprehensive. And then maybe next week or but we do something else. then I develop some detail about it. So let me assume, in other words, not for some diffusion or in some context or other, we have a log-Sobolev like this. So I'm going to write it mu now stands for some measure, some invariant measure. I don't pretend it's gamma. I don't pretend it's the Gaussian. It's some measure with respect to which we have the invariant. Yeah. So assuming that there is some constant C, positive constant C, which relative to this invariant measure mu, we have the log-Sobolev. Two C take place here of their own. With C is one. C. For this general measure, mu, I think there is a constant. And the moral of the story is that log-Sobolev inequality implies concentration. What do I mean? Give me a function f. This function of integrable, of course, with respect to mu, and one lift. Lips is continuous with constant one. What I mean is this. Say that the function f is Lipschitz continuous, it satisfies inequality like this. For some real constant f loop. When I write one lip, we're assuming that this constant is true. Look at the function f. The value of the function f at any given point x. How far away is it from the mean? And I look at all the set of all points that in which the absolute value of this difference dominates R is a positive. Of course, as R goes to infinity, this probability goes to zero. Thank you for everything. If the measure satisfies the inequality calculus, then the answer is very good. The Gaussian fantastic inequality. It's fantastic not because, not primarily, I say, of what is in it. It's fantastic, even more fantastic, on account of what is not in it. Gentlemen, what is it that is not there? I think I'll sit. This inequality is more important for what is not in it than what is in it. What is not in the inequality appears elsewhere on the block. Not in the inequality. Let me be a little more precise. On the right hand side. Oh, there is an exponential there. Something is missing on the right hand side that appears elsewhere on the blackboard, that part of the blackboard, and makes this inequality just amazing. Very. N and the dimension. It's completely free of the dimension. The upper bound depends only on the constant C that appears in the yeah, of course, I'm assuming that the Lipschitz constant is 1. I'm assuming that the Lipschitz constant is 1.
The measure.
But what appears on the right hand side? Only the constant C. The constant C in the Log-Sobolev. And nothing in particular, not the dimension. Which tells you that once you have something like Log-Sobolev, then the probabilities decay. Yeah, it cannot. Yeah, it's a stranglehold. Cannot pretend that it will go slowly because of dimension. The proof of this is extremely simple. Once you have understood it, and once you have found the right function to apply the Log-Sobolev. The right function to apply the Log-Sobolev for the infinite open. I explained this in the in the chicken calculus. You apply Log-Sobolev to this function. Here I'm assuming that the Lipschitz constant is to apply Log-Sobolev to this function. Lambda is a free positive parameter. It's a positive parameter. Near the end of the argument, because lambda is arbitrary, you choose it to be the best possible. Makes some probability as small, like the upper bound that you have there, to make it as small as possible. So lambda is a free parameter. Lambda is arbitrary. C is the constant in the inequality. F is your test function, the Lipschitz function, right? And lambda is a free parameter that at your disposal to choose. You choose it in the best possible way when push comes to shove. The end of the argument, you choose it in the best possible way. I have the details here, and we are here already for 1 hour and a half. You can read this on the road. But this is it. This is the idea. You apply to this function with left, right? The capital F is the Lipschitz function here. And you choose lambda in the first, let's see. I think lambda should be positive, although I'm not. No, lambda is real. Lambda is a free real parameter. You choose it to maximize or minimize the quadratic, the end of the bitter argument, which is not so bitter. Monsieur Ledoux has written a whole book on concentration error. So I stole the argument that you have there from him. He has a lot of stuff in there. This is what I found most appealing and most relevant to what we have been doing now. Let me, since we have come up to this point, let me not chicken out. Yeah, I think I should mention these things before we start. Yeah, let me also mention this. larger diffusion under this. This invariant number. The potential C is not just complex, strongly complex. In other words, if the Asian dominates the identity, times the raw positive constant. Then you have Poincare and Log-Sobolev. You have exponential decay of variance and relative entropy along the flow, exactly what we have been exactly. But you need this strong control. This is the condition that makes everything. What you did? We find now who applied the with respect to the inversion. When you get this amazed, just amazed. Two probability measurement mu and mu in P2 of Rn. In other words, the probability measures we find on the Borel sets of Rn, we find isolated. W2 is the Wasserstein distance between the two. This is the Kullback-like relative entropy. Mu with gamma, respect to gamma, mu with respect to gamma, and this is the Fisher input. Exactly like.
I'm sorry. I understand like, mu would be sort of like the initial probability measure.
These are arbitrary numbers.
These are arbitrary.
Arbitrary measures. These are arbitrary.
The gamma size, the
Yeah, yeah. These are two arbitrary measures. Two arbitrary.
The Fisher information defined. It's I think.
To just repeat that because somebody's watching.
you just say it out.
Just say it out loud. So the Fisher information theory definition here, because they won't be able to see it on that board. For
Yeah,
instance,
right, yeah, I forgot all of them. Exactly the same definition as before. Except now the integration. Is with respect to the new dispatch.
How does that relate to mu? Is it see if mu or something?
If it's a fun. Yeah. I'm sorry. I'm sorry. I'm really sorry. I'm really sorry. F is the radon-nicotine variable. F is the radon-nicotine. I'm sorry. I got ahead of myself. I'm really sorry. So this is the inequality of Otto and Vilani from exactly 25 years. 2000.
called HWI because it's got
It's called HWI.
because it's got the entropy,
Exactly.
the
Exactly.
W, the losses,
Yeah. It's called HWI. There is a proof of it that I really like. You can fit it on a couple of pages if you accept the result of McCann about, well, this proof is in my paper. I'm really proud of it. With Walter Schackermeyer and Bertrand Jones. So this is my favorite proof. You go read it. But I really like it. So this is called the HWI inequality of Otto and Vilani. It's the mother of all inequalities because in special cases, you get, look what you get. The special cases of this exercise. This is proved by the method of leaving everything as an exit. It's proved by that method, right? exercise, except HWI, prove the following. Arbitrary measure mu with finite second moment. The quadratic Wasserstein distance from the reference measure, the invariant measure of the non-reversible diffusion, is dominated, is controlled by the relative entropy. If they are closed in Kullback-like relative entropy, then they are closed in the quadratic Wasserstein. What's this inequality? We've already seen it. We did it in class. Talagrand. When gamma C is the Gaussian, the standard Gaussian, then we proved it in class using just say give something. Here you cannot prove it using this sum, but it falls in your lap like a ripe fruit from here. How? Exercise. And there's another exercise, you get another ripe fruit. To get that the relative entropy is controlled by the Fisher. Relative entropy now in terms of Kullback and Leibler. So you call this modified Log-Sobolev because it's not the relative entropy we have been discussing up to now, it's the Kullback-Leibler. You call this inequality modified Log-Sobolev. So this is Talagrand. This is modified Log-Sobolev. So this is more or less the entire bestiary of functional, the entire bestiary of functional inequality in this context. Plus, of course, the concentration of measurement. A lot more about concentration of measurement you can find in that. It's not a bad place to start.
Should, you mind if I turn off the,
Yeah.
turn off the Zoom, and let's think about, what's next, what do you want us to, what do you want us to do? We're here to work.
I pray for volunteers. Yeah, I pray for someone to say, I read this part of the book of Chevy, I liked it a lot, I'm going to present. If no one is ready to present, I can talk about something I mentioned in class but never did. Time reversal of the fluid.
Right.
I can talk about time reversal. It's not an easy subject. Brings tears to your eyes. But,
But it's
I have
used,
said, I have said those here in the past, I have notes, and I can go over the
Yeah.
notes and present.
and it is the state of the art in image generation.
Yes, that's the point,
And,
yeah.
and it's,
And if we want to respect ourselves, so to speak, we should say a few words about the theory that happened.
right. And then I think that there's something interesting to say after that about why it does so much better than sampling from the
Exactly.
yeah.
But before we can say anything about that, we have to understand the probability, the mathematics. How do diffusions look when you reverse time?
Yeah.
The subject of electrical engineers looked at first. A lot of things
Yeah.
in the stochastics were generated by electrical engineers. This is an example. So I'll tell you the history behind it, but then I'll give you arguments of one of the greats, Paul Bremenier, how he understood what the engineer did.
Right.